Broadcast is now starting. All attendees are in listen-only mode.
Okay, hi everyone. Since everybody is here, I would like to thank you all for attending Danfoss webinar on pressure independent and control valve, PICV, which we are doing instead of reaching you out face to face due to the current situation of COVID-19. So we will present for 45 minutes and we will leave the last 15 minutes for your questions. Which you can write it in the chat box during the presentation, and one of our organizers will take care of it. I hope you will enjoy our technical information for today, and I leave the word to our technical manager, Anis.
Thank you, Ahmed.
Thanks, Anis.
So since we will just start, so at this point you will be able to see my screen, and our agenda will be variable flow system in general, the ABQM, which is our pressure independent control valve. What is the concept, from where it came, how it improves your installation, how it saves money, how it saves energy. So if we want to start at the beginning with the normal two-way system with manual balancing valve. If we have a two-way valve, we need to balance the maximum flow going to every unit in order to modulate that flow based on load demand. But the problem here is those type of valves are a static balancing valve, which means it will be set to only one position and it will be fixed at that position. So if we take this example, if I'm trying to balance this unit, there will be overflow somewhere else. Now, if we balance another unit in the same line, more overflow would come. If we go to the next branch and try to rebalance, then again we're back to the overflow to the first branch, and so on. So in order for us to have the proper balancing at full load condition, it's for static balancing valve or manual balancing valve, also called double regulating valve, we can achieve the total balancing only at full load condition. So you can use a partner valve and do something called proportional balancing, which means if the first branch here requires 10 GPM, at the time of the balancing, we found that it is 8 GPM instead of 10, then that 8 GPM will be proportionally distributed as if it was the 10 GPM. Then later on, when we use these branch and riser valves, then we can bring back the balancing to the 100%. So this is the manual balancing part. After the manual balancing part is done, modulation of the control valve will start. And since 99 or even let's say 95% of the year, we are running our systems in part load condition. So we will never be able to have peak load condition except in that 1 month during the daytime. So the control valve will be permanently closing and opening to achieve the comfort level required by the area. Now, if the control valve is opening, again, we are back to the same first scenario, which is overflow and underflow. If you close one valve, the pressure will move to the next one. Why is that? Because again, we said that it's static balancing. It's not a dynamic. There is no automatic response to the pressure change. And if the control valve is changing in pressure difference or dynamic pressure, the authority of the control valve will change as well. And that's what explained that you have a two-way valve with an equal percentage characteristic that will turn into on-off valve. And as you can see here, with an authority of 0.3, you have like 100% wasted range. And with an authority of 0.1, it's 50% on point 3 and 100% on point 1. This wasted range, since you are recirculating the same amount of water in your installation, if you have overflow somewhere, it's underflow somewhere else. So this is, in general, variable flow system with the two-way and DRV. So if we take, why is that happening? It's at the beginning to start with how we size the two-way valve. We take a normal sizing, the flow, which is equal kV square root of delta P. Then what we need to know to select a two-way valve is the kV value, which is the flow coefficient, which is equal to flow divided by square root of delta P, or pressure drop. So if we take an example, in order to achieve an authority of, in two-way valve, the best authority we can have is 0.5 or 50%. We will explain why. So the authority is the capability of a control valve to maintain its characteristic, and it can be expressed by the formula delta P open valve divided by delta P open valve plus delta P system. So if we take an example of a selection of a two-way valve, this air handling unit has a pressure drop of 30 kPa. And what we need to have is an authority of 0.5, which means that the pressure drop across the control valve should be equal or higher than the pressure drop across the coil and the remaining of the circuit. In our case, we have 300 Pascal per meter resistance on the pipe, which is 30 kPa. We have 5 on the strainer, and we have 35 on the coil. So if we want to achieve an authority of 0.5, we need the two-way valve size selected at 70 kilopascal to achieve a 0.5 authority, which is the case in this example. Now, if we go and select the valve in the manufacturer data sheet, you cannot find your calculated kV, but you will only find the predefined or manufactured standard kVs. So in our case, we have a flow of 25 cubic meter per hour, and we have 70 kPa, which is the pressure drop we need to have an authority of 0.5. If we go and calculate the kV, we will have 29.7. And 29.7 is not a custom-made two-way valve, but the closest valve to it is 40 kPs, which is the N65. Now, this step, which will make the system even worse, is what will be the pressure drop at the selected valve kV. And in our case, it's 25 divided by 40 square, and it is equal 0.4 bar, which was initially or originally selected at 0.7. Now the authority of the two-way valve will drop from 0.5 to 0.28. And then a 0.28 authority means that, let's say, if we take an example of a linear valve, a 0.3 authority means that you will be able to control 100% open valve up to 70% open valve, which means the controllable range is only 30% of the valve controllability. Okay, so this is the meaning of the authority in physical, in real life. So if we have an equal percentage valve and we have an authority of 0.5, we are having at least 70% of the flow can be controlled. But the real life, what is happening on site, there will never be 50% authority on two-way valve for the simple reason that if you are close to the pump, you have a very high, we have a very high pressure drop available from the system. And because people, when they do calculate the two-way valve authority, they consider only the coil and the pipe strainer around the valve, but they don't consider the available pressure coming from the system. And if you are near the pump, you have available 4 bars, so your authority will be 0.1. So for that reason, two-way valve will never be able to achieve a good authority. Now, if we take most of the old project, they use the two-way valve, they would recommend, or on FCUs, on-off, on air handling unit, modulating actuator. Why? Because there is no use of the modulation on the FCUs if you have a very poor authority, because even if you put a modulating actuator with an authority of 0.2, you will end up acting like on-off because the valve will be oscillating ups and down due to the system pressure. So from this, we can understand that system pressure is a key to the proper selection of any valve, and we have to consider that. So in the next slide, we can see that 35, 40 years back, differential pressure controllers were introduced to the market for the main purpose to control and reduce the effect of system pressure. Because when we reduce the effect of system pressure, we improve the controllability of the valves and we save energy. So for us, the goal is to be able to open the valve at a very small opening in order to first achieve the required comfort level at part load condition, which is 95% of the year. Second, not affecting the overall hydronic balance and control precision. So DPCV, differential pressure control valve, is very simple. It's a valve on the return, can also be installed on the supply, which will measure or sense the pressure. It is on the return line, which will sense the pressure on the supply and close. If the pressure on supply increase, the valve on the return will close. So by doing this, you can set a minimum differential pressure that the DPCV will start operating from. If we take, let's say, 50, 70 kPa, anything less than 70, nothing would happen. Anything more than 70, the DPCV will close. We will be having another webinar about DPCV specifically because they are still useful and can save a lot of energy in case of specific projects. So if we combine a two-way valve with DRV and a DPCV, we will have a differential pressure and dependent balancing and control valve. So a PICV is the combination of all the balancing solution available as of now, which means DPCV, manual balancing valve, and then a two-way valve. So how it works, this is, by the way, this is the general concept of PICV. We will be touching on Danfoss PICV later. So it's very simple, and any PICV should work this way. There is no like different technology. It's the same. Differential pressure controller, sensing the pressure before and after a control valve, and closing and opening. There are different technologies, but the same scenario. The tube will be before the setting mechanism and not after. In that case, you will be having two opening or orifices inside the pressure control loop. and that would cause the authority of this control part of the PICV to drop if the effect of the setting mechanism is high. So now, if we see in case of normal operation, nothing would happen. If we have part load condition, somewhere else valve will close, etc., pressure will increase, and your valve is closing. The modulating valve is closing. In that case, the pressure will be sensed, and the DPCV part of the PICV will close immediately. This response time of the mechanical based differential pressure controller is less than 10 seconds, which means there is no more oscillations and pressure fluctuations in your system. The response is literally immediate. If we take an actuator, electronic actuator, which will be having a speed and the response time, the mechanical one will be even faster. So the 20, in our example here, the 20 kPa, which were supposed to be on the control valve and will affect its authority, were transferred to the differential pressure controller, and the differential pressure controller will take it. So the reason why we're doing this differential pressure controller will open and close based on the system pressure change. Why we're doing that? To leave the control part only open and close based on the temperature, the area or room temperature change. So in that case, I'm only controlling this modulating valve to respond to my load demand. Then this valve will be able, the control valve will be able to be opened at 5–10%. If I have 1,000 valves like this, and every valve I can open up to 10% instead of the two-way, which can never go less than 50%, we are saving 40% of the pumped water, which we will see in the next slide. So this is the general concept of a PICV. It's two-way valve, DPCV. Setting mechanism, same as the control part. Some of the manufacturers, they make it different than the control part. In case of same valve, control part is the same flow setting mechanism, you will be only required to maintain a fixed differential pressure across one globe, valve, and seat. If you have two separate parts, one to set the flow, one to control the flow, your DPCV of the PICV should maintain a fixed differential pressure across two valves. How the pressure is distributed between these two valves, you cannot judge. If the setting is low, you will be having low authority on the control valve. If the setting is high, there will now be a big effect, which means these kind of technologies will be effective up to 70% setting. If it is less, then it might compromise the pressure and dependency itself. But in case of, which is our technology in Danfoss, using the same two-way part to modulate the flow and to limit the maximum flow going to that unit, doing this will give you full authority at any flow setting, regardless of the flow setting, from the recommended range, 20% to 100% or more sometimes. The authority will be the same. Why? Because it's the same control part used on a linear movement to modulate and on a rotating movement to limit the maximum flow. Now if we move to our valve, the PIBCV, pressure independent balancing and control valve, is a control valve with automatic balancing function, which means DPCV plus the control valve. So here you can see clear. Lower part is differential pressure controller, upper part is the control valve, and they're just fixed together, and this we will talk about later. So here if we see how the valve is working, it's very simple. The flow direction is shown here. And if the pressure is increasing, the sensing point at the exit of the valve will be pulling the membrane down to make this cone go to closed position. When the pressure is reducing back, there is a counterbalance sensing point inside this hollow cone, and the spring will bring back the cone to its initial position. So it's not as complicated as it looks like, but in order to make the valve compact, it's this way. So in our case, we'll see on the cut piece later also. So this is the upper part, which is the modulating part, moving up and down, only responding to the command coming from the thermostat or the BMS to control the temperature. The lower part, or the bottom part, is the differential pressure control that keeps constant differential pressure independent of the system pressure fluctuation. And here you can see the movement. It should not go to full close if a DP, or differential pressure controller, of a PICV goes to full closed position. There is something wrong, either with the valve itself, it's faulty, or the maximum differential pressure of the valve is exceeded. Let's say your system pressure is, pump head is 6 or 5.5 bar, and the valve can take only 3.5. We will end up into full closed DP. And if you have a full closed DP, the valve will not work. And there are different scenarios. Sometimes it's hammering, sometimes it's leaking, sometimes it's whistling, sometimes it's having cavitation in the system. So it's really not recommended. So this is a zoom in inside the area. And as you can see here, the movement of the water sensing point, when it is going out, it is sucking the membrane with it, and then it is returning back to counterbalance in case of system pressure is back to normal. This is an example of water and pressure control animation. You can see very precise control due to the fact that there is no single excess of pressure from the system affecting the controllability of the PICV. So now we spoke about the two-way, the control part of the PICV. We spoke about the differential pressure controller of the PICV. Now we will move to the manual balancing part of the PICV, because yes, we have that as well. So the upper part on DN32 up to DN10 up to DN32, there is a gray locked mechanism. If you pull it up, you will release the rotating movement, which I was talking about during when I was explaining about different types of PICVs. So the maximum flow is marked on the valve. If we take your design flow or equipment flow divided by the valve flow, you will end up with a percentage. In our example, 270 liters per hour divided by 450 liters per hour, 60%. You just only need to pull this gray part up clockwise to reduce, and anti-clockwise to increase, go to 60%, lock it down, and the balancing is done. It's very simple. Nothing should be done, no calculation, no KV, no tables, nothing. And the setting is done. This is the balancing part. All here in the presentation, it's showing the PICV without the test plugs, because for the sake of the drawing itself, but all PICVs Danfoss have are coming only with test plug for pressure and water flow measurement using the KV methodology. So we kept the same way that DRV used to work. KV value for every setting, and then you measure the delta P, you will have your flow rate, and this is good for the test and commissioning. Now we spoke about it's a bit complicated internally, but now in the next slide, you will see that it is really not complicated at all, because with multiple parts in PICVs, one to control the flow, one to maintain the flow, and two valves and combine it together, test port, membrane, disk, etc. We wanted to have the valve, so there will be risk of a blockage. In order for us to remove that risk completely, the valve design itself is like an S-trap. So if you can see in this animation, the cone and the seat of the pressure controller part is a cylinder. It's an open cylinder from the inside, which means if you take this cut piece, the valve is only an opening, or it's a tube, let's say it's a pipe. So if we see again the animation, there is a dirty particle, it will not stuck in the valve as long as there is a flow rate. So this is our design on the valve in order to make the small side valve less risk of blockage. And till now, we never received ever a complaint related to a blocked valve. Okay, I am the one answering the complaints, and we never received that. Setting of the bigger sizes, DN40 up to DN100, same way we calculate design flow divided by the valve nominal flow. The setting percentage is given by us, so there is nothing to worry about. And then use an adjustable spanner, and here clockwise to increase and anti-clockwise to reduce. It's reverse of the small size. Plus, one turn in these valves is equivalent to 10% of the setting. If you don't have the setting scale, someone broke it, or it was painted by mistake on site, you just calculate one turn as 10%. Full close the valve, then opening turn by turn, you will get your set. For the bigger size, which is the N125 and bigger, it's the same way. You need an Allen key. It's a small opening, then you want the scale in down the side, but again, one turn is 5%. So if we take the full product range, we have from DN10 low flow up to DN250. And here you can see all these brass type are for FCUs, and we only propose most of the cases the gear type actuator. Why? Because we wanted to see the savings. We wanted to see the actual saving from the valve. So you need full modulation, full pressure independency. If you go PICV with on-off thermal, then yes, you might save on the initial cost, but you will not be able to modulate, which means you will be wasting during the running cost. But some of the application still using on-off due to the simple fact that it's a small number of units that does not require really to go modulate. We have also DN40 up to DN100, which are mainly used for air handling unit, pressure handling unit, and then 125 up to 250, which are mainly used in heat exchanger application. Now, since we said it's pressure independent control valve, you need the actuator. One thing is to notice here, all these actuators are manufactured by Danfoss in the same factory where we manufacture the valve, which means this actuator is manufactured for the PICV. There is nothing, it's not like one actuator that will work on different valves and so on. No, it's a specific actuator to that PICV. Why? As we were saying, that we are changing the setting on these valves. We wanted the actuator to be able to recognize the setting we are doing on the valve. Do so, actuator has self-calibration to suit the setting percentage that you have put on the valve. And this is achievable because most of, let's say, old actuator, they have limit switch at close position in order to protect the motor from overload. So what we did simply, we didn't make hardware, we make it processor based, and then we put 2 limit switches or end travel limit switch, one for the full open, one for the full close. By doing so, if you set the same valve, the same size at 2 different settings, you put 2 actuators on them. This actuator will modulate that percentage. That presetting, the other actuator will modulate different percentage. So regardless of the setting you're putting on the valve, the actuator will only modulate the setting you have done. And there will never be gap between the spindle of the valve and the actuator operation, because if there is a problem in controllability, and the lifespan of your actuator will be also compromised. Let's say actuator is designed for 100,000 cycles. If you have a wasted range of 50%, that is half of the lifetime of the actuator is gone. So you need the actuator to only modulate the stroke of the valve. Clear? So another feature which is very important, if we are having water to air exchange, which is FCU, air handling unit, pressure handling unit, you need the control valve to be equal percentage. Why? In order to counter the coil characteristic to achieve the linear control characteristic between the signal and the cooling output. So the end relation between the valve and the cooling output should be linear in case of water to air exchange. In order to achieve that, you need the valve alone or the valve with actuator to be equal percentage in order to counter the coil characteristic, which is parabolic. Okay? So if we take the lin log alpha, which means you can select what will be the characteristic on your control part of the valve. In our case, both are available because this PIBCV can be used in application where water to water exchange or in application where water to air exchange. And that is very important to have in a single valve, because if you don't, then you need a complete model of valve for AHUs, FCUs, and another model for shield beams, radiator, heat exchange. In our case, you can achieve both by using the combination of the valve and actuator. High rangeability, if we take the smallest actuator we have, 256 steps. The minimum of the smallest actuator is 256 steps, which means if your valve total stroke is 2.5, it will be divided by 256. Then you can move your valve spindle by 0.01 millimeter if required by the control sequence, because in case of a normal control sequence, you have a half volt movement, half VDC. In some of the BMS application, this can go up to 0.01 or 0.02 VDC. In both cases, the actuator can respond to that. Now, if this is the case of the actuator used with up to the N32. If we take actuator used for the N40 and bigger, we have a 1,024 steps. 1,024 steps, which means, again, the bigger the stroke length, you need higher number of steps to achieve the same control precision, which is 1,000 to 1. This is the rangeability that we are specifying. Selection is done by Danfoss. This is something that we do, sizing, selection of the valve. And it's also easy. You can go and cross-check any selection. Just draw the line of your flow, and you will be crossing different size of the valve. Calculation. Here, worth to mention that we are doing this in Danfoss also. Calculation of the pump head differential pressure transmitter location and set point. We are doing it to support our customer and to make sure that system hydronically is sized and selected properly. But in case you are doing it, just determine the critical unit, calculate the pump head without the valve, then add the static pressure of the PICV, which is between 16 to 30 kPa. Application, air handling unit, Pancol unit, heat exchanger, most known application. So how the valves save money? No calculation required, no KV calculation, no authority. Mounting, if we are using PICV in your terminal unit, no need to use any balancing valve in the system. It's no more required because the PICV has its built-in automatic balancing function, which will do the job of a manual balancing valve. So every balancing valve in the system can be removed. So how it saves energy? If we take the example of the pumping, this is a comparison between a three-way, two-way, and the ABQM, PICV. So the three-way is simple. It requires full load, full head. So it's the most consumer energy in euro per valve per year. Now, if we take the example of a two-way valve, in two-way valve, you need a higher flow and a higher head, which means to achieve the same comfort level, you need to pump more at a higher head. And why is that? As we said, if we try to modulate two-way valve, which has a poor authority, let's say 0.4, then we will be able to modulate from 100% to 60%. While with PICV, which can go to 10% even opening or less, then the difference between 60% and 10% is 50%. And that's what explains in this table the cost of the PICV on energy per year is half the cost of a two-way valve. And this is the effect of the running cost. Chiller. Here it's showing that if we have multiple chiller on a common header, if it is consuming less energy if you have one chiller running at 100% other than two chillers, each of them running at 50%, because of the starting current, because of the design parameter of the chiller, which will be changed if it is if you have overflows in your system. So if we take an example here, in order to simplify the energy saving on the chiller, every chiller, let's say, require a suction temperature on the compressor. And what the compressor will be doing will be compressing the gas or the refrigerant to the condensing temperature. Let's say if we take a 12 degree is entering the compressor, you need to heat it up to 40 or 42 degrees condensing temperature. Then the compressor will require, let's say, 0.7 kilowatt per ton to do that. Now, because of the overflow in the system, the suction temperature of the refrigerant will drop. And if the suction temperature of the refrigerant will drop, the compressor will require more work to do to heat up a 12 degree to 40 rather than 9 degree to 40. So that is why in the district cooling application recently, they are applying surcharges. Why? Because these surcharges are due to the low delta T from the building. So it's simple. Compressor is designed to compress refrigerant from 12 to 40 but because of the overflow in the system, this 12 is dropped to 9. Then the compressor will need more energy to heat up or to compress 9 to 40. So that is from where this saving would come. So 3 degrees on the return temperature is direct more than 10% total cooling energy saving, which means 10% on one chiller, which will have like 150 kilowatt, is equivalent to the total energy required of the pumps combined, which means like you are having 10% on chillers is equivalent to 100% on the pump. The last part of the saving is the comfort level. So now in normal two-way valve, we have a unbalanced system, which means that the flow will be oscillating ups and down due to the pressure dependency of the two-way valve. And if you have unbalanced hydronic system, you will have unbalanced also thermal distribution, which means some of the rooms will be feeling hot, other rooms will be freezing, regardless of the set point on their respective thermostat. Now we stabilized the flow in the system, and then the temperature also will be stabilized, which means you can move inside the comfort zone by increasing the setting on the thermostat from BMS without affecting the comfort level, because as a human, we will be feeling either it is hot or cold. We cannot feel it's 23.7 degrees. This exercise we did in one of the hotel, and it was like 2 degrees. The effect was huge. Why? Because they have like 30% of the hotel as common areas, and those common areas there was no control at all. Like it was linked with BMS, but actuator is not working, the valve is kept at full open, the control is only on the fan. Some of them are set to 19 degree corridors, etc. So what we did, we changed this with the PIBCV and actuator, we put the proper setting, and it saved a lot of money. Like if you can see from the last line here, 1 degree on the set point is 10 to 16% of the total cooling energy. So if we take 2 degrees, that's 20%, and 20%, if you take it as 30% is the common area, that's a total of 7%. And what we have done to get this 7%, actually nothing. It just increased the setting. And how this 10 to 16% can be proven, you can go to any heat load calculation program and size your unit with a unit set point of 23, for example, and then size it again with 22 and see the difference in MBH. And how we convince the customer to do this? By simply mentioning that the corridors, lift lobbies are walkways. You will never find a guest sleeping there. So even if you put these areas at 25, no one will complain. But if you lower the setting there, and your guest will be going in a corridor of 21, 22, entering his room, which is 23 setback temperature when you remove the card, then he will complain the room is hot. While if you keep the room 23, increase the corridor 24, you did nothing, only change the setting, and there is no complaint. So it's our nature, how we feel, the temperature difference, which will make us complain or not. So summary, by reducing the overflows, the pump can run at lower speed. By improving the delta T of the installation, efficiency of the chiller can be improved. By increasing the performance of the control, the temperature set point can be optimized. Now, this is it from the presentation. We are exactly according to the time. And now, if you have any questions, I think my colleague got some questions in the chat box, and feel free to share them with me so we can answer those. Ahmad or Mina?
Okay, Anis. Thank you so much for the technical information. And we will start with this question. Do we require rebalancing when introducing PIBCV valves?
Again, do we require rebalancing?
Yes.
No, because, yeah, with the PIBCV, before installing the valve itself, you are setting the flow, which means the balancing is done during installation of the valve. Some of the people, some of the installers, they fix the valve at 100% because they need to do the back flushing. Then they set the valve. But the balancing in case of a PICV is done one time only. No rebalance. You don't need to revisit the valve. It's one time, either during installation or after the flashing. It's up to the installer. The installer required flashing, or if the installer required to set the valve before installing it. So it's only one-time operation to set the maximum flow as we shown in the slides, and that's it. So no rebalance required if you are using a PICV. Now, if you are using a mix between PICV and DRV, you might need to do the rebalancing on the DRV if in your project you have both. Let's say you have an existing project with DRVs and two-way, and you decide to change partially or one phase, you will put PICV, and it is within the same loop. PICV will have the minimum required differential pressure to give you the design flow, while DRV was balanced based on the overall system pressure. You might need to visit the DRV, but the PICV still, you don't need to do anything except the setting before installing the valve. Did that answer the question?
Yes, I think so. Yeah, next, so how is the pressure from the control valve transferred to the DPCV?
Okay. So as we said, if you know about any expansion valve, there is kind of capillary tube. So there is a small tube connected before and after the control valve of a PICV. The control part of PICV, there is two impulse tube or capillary tube or copper tube you can call, that if the pressure is increasing upstream, the valve will close downstream. It can easily be seen in the first slide which we were shown. I will quickly return back to it. And simply, what I was talking about is this part. This copper tube is linked directly with the pressure chamber. Another tube is linked with the lower pressure chamber. So if the pressure is high, it will go through here and push this part to close. Now look at the DPCV part, it's bent till down. How this is done? Pressure is pushing a membrane, EPDM membrane. The EPDM membrane is linked or fixed on the disc. So the membrane is pushed by pressure of the water. It will drive the disc. The disc is linked with the pressure cone of a two-way, normal two-way valve. Then it will close. So the sensing point is this tube, which is from here till this point. This is the sensing point of the PICV. Then if the pressure will decrease, this is the counterbalance pipe or tube, which will drive this disc and membrane back to initial position. Who would define the initial position is the compression ratio of this spring, because every DPCV needs a spring. Clear?
Okay, another question.
Any more questions?
What is the cone material?
What is?
The cone material.
Cone, yeah. We have these are brass material for the small size. In the control part, these are and the seat is Dizadar as well. In the DPCV part, because the valve is a combination, which I will show here. Yeah, this one is the brass, and the seat is Dizadar brass. The disc and the cone of the pressure controller is stainless steel. The spring is stainless steel, and the membrane is EPDM, vulcanized. So this is for the size up to DN32. For the size DN40 and bigger, you have also stainless steel pressure controller cone. These are brass two-way part cone. This is up to DN100. For DN125 and bigger, everything inside the valve is stainless steel. All of the material except the membrane of the pressure controller, which should be, it has to be EPDM. So yes, we have either stainless steel, brass, these are dark brass. So it's only metallic internal material. We don't have plastic. If that would answer the question.
Yeah. And another question also, would it be necessary to readjust the setting on the ABQM as the equipment age and the efficiency of the coil might change?
Yes, you should keep like 10% safety on the flow setting, because after years of operation, there will be a drop in the efficiency of the cooling coil. But why I said 10%? Because the coil is manufactured to give you that cooling level. If you give 200% of the flow, or if you give 10% extra flow, you will get only 10% extra cooling. Because when you reach the limit, the maximum limit of the cooling or the energy output from a coil, you cannot exceed that. There is no relation that if flow is 200%, cooling is 200%. No, there is a limit, and the limit is max capped at 10% to 15% max, which means you just keep 10% extra safety on the valve setting for the future. If you want, after 5 or 10 years, if your coil efficiency is dropping, you can increase that 10%. Even if you put it since day one, it will not affect, because the actuator will modulate the spindle regardless of what is the load demand.
Okay, and we have this question: what is the calculation for the TDS location and how it is affect with the pump control?
Yes, this is let's say a service that Danfoss is doing. It is for your reference. It's not something that we are dictating. We are just assisting with the sensor location, differential pressure transmitter location, which we see is the most efficient for the energy saving in your, let's say, because what is the best recommended location of a DP transmitter will be at the last point. So in our case, we have the software. We can put the drawing, your drawing, in real size, pipe and schematic diagram. Then we can calculate the critical unit. We can calculate different sensor location and set point in order to help the project itself. So, but usually this is done already. It's like a title of verification. Sometimes they're telling to only us should do it, the valve specialist should do this calculation, and it is submitted for approval to the consultant. So yes, it's what you need in order to define your critical point and your differential pressure transmitter location and set point. This will be used to control your pump increasing, ramping up and ramping down. And you need that in order to minimize any over or excess of flow, even with PICVs. If you have, let's say, we know that 100% will never be exceeded by PICV, but less than that, if you will be able to run your system at 30% and you are running it at 50% due to wrong location of the DP sensor, then this calculation might help.
Okay. And yeah, next, what is the advantages of Danfoss PICV compared to other PICVs or other brands available in the market?
I would name a simple advantage is we are having our own valve and actuator, and we are having the combination itself of the valve. Let's say most of PICV manufacturers, they will be having either the valve or the actuator, and they outsource the other one. In our case, the valve can be used as linear and equal percentage. The valve have full authority at any setting, and you cannot find this anywhere else. Having the full authority at all the settings, people can mention it, but we have the graph showing the curve characteristic of the PICV at 20% setting and the characteristic of that same PICV at 100% setting, and it is showing the same characteristic. Why? Because we are using this stroke limitation technology, which is using the same part to modulate the flow and to set the flow. So if you rotate the valve, you limit the maximum opening, and then if you push the spindle, you open and close the valve. Doing so will give the differential pressure part only one single job: maintain the pressure difference before and after the control part. So this some of the advantages. Another important advantage which we need to talk about is the capability to change the control characteristic. Again, if you have a valve mechanically equal percentage, there is a high chance that this characteristic might be affected by the system hysteresis, they call it, because the valve will be vibrating internally due to the proportional band, and it might open, close, but in a level of plus minus 10 to 15% during the curve, but the curve will look like equal percentage. In our case, it's a software-based equal percentage characteristic, and that will make the valve having a perfect equal percentage or linear based on the application. The last but not least is the material itself and the internal design of the valve. No risk of blockage and no plastic internal parts. So this is a couple of the advantages that we have. But we have specifically, like we have a full list. If required, we can send project based or based on what exactly you need as a comparison we have.
Okay. Yeah, another question. Shall we consider the static head of the system while calculating the delta P range across the valve?
Static head, no. It's only dynamic head.
Okay.
Because static head means, let's say, if you have 16 bar, then 16 minus 10, that is 6 bar. So this is a static. But if you take dynamic, you have, again, you have, let's say, 6 or 7 minus 1. So it's static, you need for the pressure rating, the PN rating, then you need the static head. But when you are calculating, you need only the dynamic head, which is the pump head.
Okay.
Okay.
And another question, when I need on-off actuators, still 0 to 10 volt required, or I can use 230 volt AC?
If you will go with on-off?
Yes.
Again, the question, if you are using on-off?
Yeah, when I using on-off actuator, still 0 to 10 volt required?
No. On-off will only work with either 230 or 24. No command, no 0 to 10 volt required at all. It's only open and close.
All right. And is it possible to verify the flow rate through the control valve using DP, or do you have accurate KV values?
No, for measurement, yes, we can measure like the RV using the KV methodology and so on. Now, accuracy, it depends. Like if it is at the higher side, the accuracy will be better. If it is on a lower setting, the accuracy will be less better. But let's say we say plus minus 10% is the accuracy that you should consider. plus minus 10% in normal operation. Sometimes go 15 based on how the valve is in the project. But yes, we already did a lot of projects with the flow measurement using the KV methodology on all sizes. And some of the projects I saw 5% accuracy, which is perfect. Other projects I saw 10, which is still okay. Some I saw 15, but 15 and 12% was only on a few valves near the pump. And that was because of they did not optimize the pump yet. But in some of the projects that we did the commissioning, we were able to achieve from -5 till +10 as an accuracy, which is perfect and approved by every test and commissioning party. Yes, we can measure the flow. That is to answer the question. Yes, flow can be measured like any DRV.
Okay, and we have this question: PICV of a smaller size have 2 test ports, while larger sizes have 3 test ports. Can you tell us why? What is the reason?
The main reason is the size of the valve itself. You cannot fit 3 test ports on the small size. A big one, you can. There is a space for that. But the difference between the 2 and 3, on the 3 test port, you have before and after the whole valve, P1, P3, you have before and after the control valve, P1, P2, you have the before and after the differential pressure controller, P2, P3. So here you can measure 3 DPs. It is good for, you can measure the flow using KV methodology, and extra, you can measure available pressure across the whole valve and the available pressure across the DP part. What is the valve resisting to what pressure from the system? It is good for troubleshooting. But for the flow measurement, all the sizes you can measure. On the small sizes, you have 2 test ports due to space. We don't have enough space for that. And these 2 test ports can be used only to measure the flow with the KV methodology. So on the bigger one, we have a space, we put 3. On the small one, we don't have, we put 2. But we made sure that regardless of the size, these 2, at least 2 of the test ports will be measuring the control part of the valve differential pressure, which is used for troubleshooting and flow measurement.
Okay, we have another question about the clearance before and after the PICV. What is the minimum distance to be maintained to install the PICV?
Yeah, usually there is the requirement of this distance is on proper measurement on orifice plates and DRV. But the PICV, it's already pressure balanced. And when you are measuring across the control part of the PICV, you are actually measuring a stable area, because any fluctuation and excess and coming from the system, the differential pressure controller will resist. So these 2 test ports from where you are measuring have really a smooth running water. And for that reason, we say that there is no pipe clearance required before and after the PICV. No 10D, no 5D, nothing. You can put the valve directly after an elbow or before a T. So it's no restriction, no clearance required for the PICV installation.
Okay. Do we have to do any periodic maintenance for the PICV and the actuator?
No. Simply,
No.
the valve is maintenance free. There is no requirement for any maintenance to the valve or the actuator. You don't have to clean, you don't have to check, you don't have to do anything.
Okay. What is the maximum and minimum size of PICV?
10 millimeter, 3 by 8 inch is the minimum. And then 250 mm, 10 inch is the maximum.
Okay, and what about air inside the PICV? How will be sure there is no air during testing?
Usually the system, they de-air it. The installer, they de-air, because if there is air inside the PICV, it will not have an effect on the PICV more than the effect on the system and the pump, because the small air bubbles will become like a big cavitation when reaching on the pump section, and this will destroy the impeller. So, but if there is air on the PICV, you can just push. If you want to purge it out, you can push the spindle of the PICV multiple times up and down, then you can purge any air bubbles inside the valve. So it is not really something dangerous to deal with, but it will be dangerous in case it reaches the pump. So that's why you have the air vent, manual air vent or automatic air vent to clear that air from your system. And not PICV is not a really big deal.
Yeah. Okay. Will the ABQM be able to prevent the overflow if the pump are running in at too high speed due to poor pump control?
Yes. But if, let's say, if there is somewhere where this would go, yes. But if you tell me, then the pressure overall of the system is higher than the requirement. We have on the valve, the PICV will be able to give you your design flow up to 6 bar dynamic pressure. Maximum differential pressure is 6 bar. So if the pump head is 6 bar and you have pump running against one PICV, the PICV should be able to give you your design flow. So yes, it can still give you the system minimum system set flow, even if the pumps are running at 100%.
Okay. If we are replacing the control valve, two-way valve, with the PICV, is it enough to open the DRV to max setting, or do you recommend to remove the DRV from the system?
Yes, if it is there, and when you open the DRV full, and the pressure drop across that DRV is very less, then keep it. But if you put the DRV at full and the pressure drop is still high, that might affect your available system head, then remove it. But usually you can, most of the case, you can just full open it in order not to make a lot of big work done, because usually a PICV will fit directly on a two-way valve. If you remove a two-way valve, put PICV, it's nearly the same size. If you match the size, it will be the same width. So sometimes they said, yeah, why we should remove the DRV, just full open. Yes, it is possible. Subject that most of the time DRV's pressure drop is very low. So yeah, you can full open the DRV and keep it. But if it is as high as it will be, PICV plus DRV higher than the existing two-way plus DRV, then better remove the DRV to reduce.
Okay. And we have this question: in multi-story building, is it possible to replace the existing two-way valve on the main headers and the AHUs only, without replacing for each individual fan coil unit? Can we get the benefit from replacing these valves only with considering keeping the existing two-way valve on the fan coil unit?
Yeah, based on the ratio of these air handling units or the big valves, what is the flow they are passing? Let's say if it is 50%, you will put 50% of the flow is going through these valves. You change them to PICV, you will get 25% saving by changing to PICV. 25% out of the 50%, that's like 15% or 10% total saving. So it's something that you will be calculating if you are choosing a phased replacement. You change here first, then change there first. But if savings can be seen even if you put a single valve, you can see the difference. One single valve, you can see the difference on the saving.
Okay, and we have one question on the country of origin for the product and the valve body.
Both are Slovenia, Europe.
Yeah.
Valve and actuator are from Slovenia, and it is made in Slovenia, which is part of the European community.
Okay, and we have a question about the minimum flow setting. If the flow rate is 20% of the flow rate, like, is it okay to select this valve considering 20% presetting?
Based on how we are setting or testing the valve in the factory, if we say 20% minimum recommended, we can achieve that. But our testing rig is not the project. After time of operation, the project at 20%, there might be a lot of things that will affect even. So yeah, if a 20% is your design flow, then yes, you can put at 20%. But if I have a unit if I have a flow of 0.01 liter per second, I'm sure that this flow is the design flow. Then I would go to the equipment flow, which will be around 0.03, and try to increase the setting a bit, because then the actuator will modulate and control back to the 10% or 20% required. So yes, but I only see this smaller flow on a telephone room flow rate or electrical room on the floor level. It's not really very, you can see a couple of units, but usually minimum setting I was able to see was like 20%, but on DN15. Then I changed it to DN10 low flow, and the setting became 52%. And that is how I made it on the safe side, because I wanted to leave some safety on both sides, on the lower and higher end of the setting range. Clear?
Okay, and yeah, if we have flow rate higher than our maximum flow rate for size DN25, is it okay to use two valves, two equal sizes?
You mean DN250?
To cover the flow rate? Yeah.
Yeah, two PICVs in parallel will work, subject to the control people to know how they sequence them. Either they sequence them on one valve first and then second one, or simultaneously both will be opening and closing. Yes, it can be done. If you have the space, yes, you can put even 3 in parallel, no problem, as long as it will match the flow.
Okay. I think we are almost done.
Yes, okay. Already
Okay,
we are keeping the people more than the time by 13 minutes. Yeah?
Yeah, we are trying to answer all the questions. So we have here a question. If you are using PICV, do we still need to install three-way valve on the fresh air handling unit?
It's not,
or it's not
do
required?
we still need? What we say, we should not install a three-way valve if you are using PICV. Because as we said, most of the time the system is running at part load condition. In case of a three-way valve, when it achieves the load, it will bypass the flow. When you bypass the flow, you will reduce the return chilled water. When you reduce the return chilled water, we are back to that chiller case. Your return temperature will drop, you will consume more. Higher flow, low return equal more consumption. So if you are using PICV, the best practice is to make a bypass pipe, okay, with a bypass valve. This bypass valve will be normally closed and will open only if the pump is going less than 30%. One pump is going less than 30%, you open this bypass. Otherwise, it should be kept closed all the time, and the system will use only PICVs. You should not mix three-way with the PICV. It will only cause problems and low delta T during the part load condition.
Okay. Still, we have many questions. We will take the last question, and then we will reach out to each customer regarding the remaining questions. So this is the last one. The delta T controller valve will be on the upstream or downstream?
Okay, I will answer this. For the sizes up to the N32, the differential pressure part is coming first. And then the control valve is coming second. For the DN40 up to the N250, the control valve is coming first, like the drawing I'm showing here, and then the differential pressure controller will come after. Why is that? It's simply because up to the N32, it's a compact one. So we did, instead of here, as you can see in this graph, that the pressure of the water is pushing the disc and membrane to close. While if you see on the small size, the system pressure is pulling the membrane to close. One is push, one is pull. This is one is like a section here to close. The other one is a push to close. So this is, we are talking about pure pressure here. So yes, on the small size, the downstream DPCV. On the bigger size, upstream is the DPCV, like this one. Okay?
Okay. Okay. Thank you, Anis, for the presentation, and I hope you enjoyed our presentation and it was useful for everyone. Any feedback or a question, you are welcome to reach out to Danfoss Seating team, and we will arrange a few technical webinars on the next few weeks. So we wish you will join us also. And thank you so much.
Okay, thank you.
Thank you, Anis.
Bye.